This is the 8th video in the series on converting and displaying a video on the Commander X16. Let's just have a quick look where we are. We got quite a bit done so far. Last time we converted a single palette and saved it. So this time we're going to be converting an image to a tile map. But before we get into that, we're going to modify a couple of subroutines and change some labels around. And then we're going to convert single bitmap into tiled data. So for each row and column of the bitmap, we got to set up some pointers in to point to the destination within our tile map of that data, and then we got to actually move the data from the bitmap to the tile map. And then once we've done that for each row and column, then we can save the image file. So let's get right into it. First thing I want to do is I want to change a couple of files here. First of all, svid, I don't want this. Let's go back here to lvid. Oops. I don't want it to call vid plus. I don't want it svid to change our file number. I want lvid to do it, but I don't want svid to do it. So I'm just going to change this to a jump save and delete these 2 bytes. Also, svid and lvid are kind of badly named. They're not saving a video, they're saving an image. And lvid is loading an image. I'll leave vid plus the way it is. I don't care about it. Okay, so next one I want to go to lpal. Okay, so I only want to call lpal, which loads the palette, on the vsync. So if I go to my custom IRQ, I've got to assume that SIRQ has been called before lpal has been called. So what I want to do, all our custom IRQ does, SIRQ will just set up so our interrupts go to the custom IRQ. All this does is loads VISR. What's VISR? Well, if we go to the Vera Programming Reference Guide, VISR is just the label I've given to this address here, which is the Vera interrupt status request. And all we're really concerned about here is this bit right here. This is bit 0 of this. So our custom interrupt just takes that and stores it at temp1 and then just goes to the normal interrupt subroutine. So if we go back, what I want to do here is have this call that interrupt. How do we do that? Well, I'm going to insert 6 bytes here. Dead air, lovely. Okay, and I'm just going to copy this down to here. Up here, now SIRQ, that has set the interrupt disable, and it hasn't re-enabled interrupts. So the first thing we want to do is clear the interrupt disable bit, and then wait for an interrupt. And then we'll set that interrupt disable bit again. So now we've got in temp1, we've got whatever was stored in that VISR register. So now we're just going to look at bit 0 of that. So we can use the bbr0 command, but I'm going to be branching to an absolute address rather than a relative address. So I've got this little sneaky shortcut here. It's temp1 where we've got that stored, and we want to branch back to lpal. So what this means is if our interrupt was not triggered by vsync, we don't care about it, and we're going to branch back to lpal and wait for that vsync. So that's all these 6 bytes do, is wait for a vsync. And then it'll load the palette. It's only 512 bytes, so that's very fast, and it'll happen in the blank right after the vsync at the bottom. And then what it'll do is it'll look up its palette file number and load it. And then based on that palette file number, let me just look at this in mode 2. Based on that palette number, if the palette number is even, it loads, shows one set of tiles. Palette number is odd, it shows the other set of tiles. So that's what all happens immediately after the vsync. It loads that palette and shows the appropriate set of tiles. And then, go back to mode 1 here, then it branches to pal plus. And I don't want saving the palette to increment the palette number. So we'll just jump save here. And there's no point in branching to something I'm only using once. So I'm going to insert 5 bytes here. And now I'm going to move pal plus to 0BC9, 7 bytes. Okay, and we can delete these 7 bytes. Okay, so now if I go to lpal, it doesn't branch to pal plus, it includes pal plus, and now spal doesn't have anything after it. So one other thing I wanted to do, let's go back to spix, is I've been doing something wrong on my memory map. That tile data isn't all the way to 6DFF, it's to 6CFF. It's only 45 pages of data. So we have to change this here. So now that will correctly save the correct number of pages of RAM. It's now going up to 6CFF instead of 6DFF. Okay, good. Now, next thing, we got to convert a palette. Oh, not yet. I wanted to go to 0060. Temp 1 and temp 2. I've been using these 2 bytes as the low and high byte of a source of any kind of data. So I'm going to just change these labels here. And temp 3 and temp 4 I've been using as a destination. So I'm going to change these labels here. Okay, so now if I go to something like here, xcall, instead of pointing to temp 1, temp 2, now it's going from source to destination, and this makes a lot more sense. There's nothing that has changed in the code, just the way it's displayed because the labels have changed. So next thing I want to do is, the main point of this video is to convert a bitmap into tile data. So for each row and column, we've got to find our pointer for our destination for our data. Let's go back 0060. You can see I've got 2 bytes set aside here, row and column pointers. So if we go to G/RC, this gets an address from those row and column pointers. So what it does is loads X with the row and Y with the column. And then we've got those 2 lookup tables from way back when, row L, row H, and call L, call H. So we take the row address low and we add the column address low, column offset low. So this takes the row address, adds the column address, these are low bytes, and stores it in dest. Then we take the high byte, and note that we're not doing anything with the carry flag here. So if row L plus call L is greater than 255, the carry will still be set at this point. We load the row H That's the row address high. You can see it ranges from 40 to 42. And we add, according to whatever value y is, we add the column offset high. So this gives us an address. A high byte then gets stored in destination high. And so now destination and destination high have the address of our destination byte. So now, converting the image itself, we need to store 7400 in source high and source low. And then we load 43 and store it in row numbers. So 43 in hex is decimal 67. Remember, bitmap files start at the bottom left instead of the top left. So we're reading one row at a time, but it's the bottom row, then the second from the bottom. So we have to start at the bottom and work our way up. So we stored 67, decimal 67 in our row number. We store 0 in our column number. And from that we call g/rc, which determines our destination address. Then we load indirect from the 0 page address at source and store indirect at the 0 page address at dest. And that takes care of moving the data from the bitmap to the tile data. Then we just increment our source low bytes, and as long as that's not 0, we'll skip this line which increments the high byte. If it is 0, then we'll increment the high byte. Then we increment the column number, and if the column number is equal to A0, then that's 160 columns, and we're done the entire row. So as long as we haven't reached 160, we branch back here to getting the next row and column pointer converted to an address. Otherwise, at the end of the row, we decrement that row number. And as long as that row number is greater than or equal to 0, it will branch back here to where we set the column to 0 and the process starts over. But once we've decremented to FF, it'll just jump to saving the picture. So now at this point, we've made a bunch of changes, so I'm going to save the file. And now we'll execute our test program, which just sets the values from all of those 0 page variables to 0, and then it will convert a picture. Well, actually, before we do that, we need a picture in memory. So let's load a source picture. Okay, we've got our image 1 in there now. So now we can execute our test. And if we go into our Star Wars folder, we can see we've got a new file there. It's v000, etc.dat, and it is 11,522 bytes. So that's a 2 byte header plus a 160 by 72 tile data. And that's it for this video.